Welcome to part 5 of Demystifying LLMs for software developers. I see the title is still the old title from the presentation I gave last week at One More Thing conference for Swift developers using MLX. This is the last video I am recording today. So the next videos will be based on what you as a viewer would like to learn or to see. I will mention it again at the end of this video, but for now, let's go and check out the sampler or the non-deterministic part of the LLM. So we have seen in the previous videos that tokens are the ASCII or Unicode of LLMs. Embeddings are the GPS coordinates of tokens. Transformers, they take in embeddings and they produce an array of logits, the size of the exact size of the token array. And transformers and the tokenizers are all deterministic. And we add randomness to make LMs feel more human-like. And that's the part that we're going to discuss in this video. So far, all the previous videos, everything was deterministic. In this talk, we're going to add like the non-deterministic random part. And again, the way we describe like LMs is we assume the transformer is a black box. We have some processing before the transformer and after the transformer. Out of the transformer, as I just said, comes out like an array of logits, and we're going to process that in a way that produces a next token. So the sampler, let me just go to the source code of Llama 2, the app that we've been using, the inference engine that we've been using as an example. This is all C code. So it is not a ton of code. It is probably like 200 lines. And you can see there is some random and some other things going on here. So let's go through what we see. So again, like the goal is to make LM feel more human-like, to add some randomness instead of like always returning the most obvious choice as the next word. So one thing to remember is since like the result of each token is fed into the transformer again, like iterative task, it does mean that if one word is different, non-obvious words, that the path for the next words can be very different as well. So they can like diverge pretty fast. So we've discussed this in the previous one. So this is what we ended up with. So if we have a prompt, the sky is, then the most likely word to follow is blue, but clear is also pretty obvious. And then we have a number of words that are less likely. Again, these numbers are not real numbers. I was lazy. I just typed them in here. What is important though is that the logits, because these are the logits, is basically an array of exactly the length of the tokens, and the index of each logit corresponds with the index of the token. And as a reminder, the token index is right here. So the word settings, for example, has this index right here. Okay. What do we do with this? Because the logis is kind of a raw value. It can be negative, it could be positive. It's all over the place. As you probably have guessed, so it would make a lot of sense to normalize this into distributions. And if you are very familiar with LMs, this is the point where you would say, well, actually, I know that the order that I'm explaining this in is not the exact order that happens in the LM code, and I will get to that in a bit, but I think this makes it easier to understand. So softmax, basically what it does, and this is a little bit simplifying, it normalizes the scores. So instead of like positive and negative numbers all over the place, you'll get an array of values, and the sum of all these values is exactly one. So basically, it means that again, these numbers are not real; these are made up by me. That blue now has a 42% chance of being randomly chosen, and clear at 23%. Um, but oh yeah, so since the original talk was meant for Swift developers and MLX, and that's definitely like something I'm gonna explain in later videos because I think MLX is one of like the hidden gems of Apple when it comes to AI. This is a softmax, so basically the normalization plus a little bit more of the logits. This is not like a lot of code. It is pretty basic. Now let's go to the options that you can set, and we're all familiar with these, like temperature. Those are the things you can set in ChatGPT and the OpenAI API, etc. But what does it mean? Now, usually we say like the higher the temperature, the more creative the answer is. But what does it mean like in code? Well, if a temperature equals one, there is no change to the probabilities of the distribution of the tokens. It will still be blue was 42% chance, it still is 42% chance, and the rest of the numbers are the same as well. The temperature one is no change. If we set it to zero, what will happen is that the most likely next token will have the value of one, so it will have basically a 100% chance of being chosen, and all of the other values will be zero. A higher temperature, say temperature equals 2. Now what we'll see, and let me just go back to the original one. These are the original numbers, so 42% for blue and 5% for gray. And now we see that the least likely next tokens will be increased from 5% to 11% for gray, for example, and the most popular tokens, the most likely tokens, will be downgraded basically from 42 back to 33, which means that the less likely tokens have a higher chance of being chosen in the end than before. So that's basically what temperature does. What does it look like in Swift? Again, it is not like a lot of code. But what you see here is something that I referred to earlier, and that's the order. The order that the temperature and the softmax is applied is actually exactly the opposite of how I explained it, because the temperature is applied first, and then the softmax scales everything back to in a way that the sum of all values is equals one, exactly one. Um, there are two other ones, top K, also known as top N, and top P. Um, top K again, it is ridiculously simple to explain if you understand like what is happening. Um, Basically, what happens is it's top K keeps only the K tokens, K the number, huh, that's an integer, with the highest probabilities. So, for example, if K equals 1, that's actually the same as temperature equals 0, because the most likely next token will only be have one the value one. The I should explain that top K. The function, the method that does that calculates top K, it does return the same length array as it is presented with, because you want to keep the indexes of all the tokens. So you have to keep the length of the array from the logit all the way in this process, exactly the same length, the same number of items in the array, because we use the index of the array to refer back to the token. And again, so if the most likely word is blue, for example, then in case top n would be equal to 1, then you'll have an array of like 20k values that are all 0, except for the item in index 9539, that will be 1. Top P is basically the same, um, but the top tokens probabilities add up to the floating point value that you passed in top P. The code for Swift, again, it's pretty basic. It's not very hard to understand. Um, this is basically how it looks like, and this is how it works. So you can set all three, because it's basically like the temperature is set first, the softmax is applied, top n is applied, and then top p is applied. And based on like numbers, I think you get like a feeling right now what these effects are of on setting these values. Um, so once all this is done, we basically get to the random function, and this is the randomness where blue, for example, this is after again these numbers are not the real numbers. I just made them up, but they are like what they could be. Um, so in this case, like blue has a 33% chance of being chosen, clear 24% chance of being chosen, and gray in this case will never be chosen. And that is basically how the whole thing works. So it is not very difficult. And once the token is chosen, how do we get the token, the value of the token back? Again, it's the index. We pick the index of the chosen token and check that in the lookup table for the tokenizer.json. So in this case, if the token is indeed blue, it's the index of the word blue. And once we have that, the sky is blue, then this sentence will be passed into the transformer again, and we do the same thing all over again. Now then the question is, when does it stop? And that is explained best if we make slight detour like how LLMs are trained, because we train them with basically text from the internet. And the text from the internet has like a beginning, and actually we see that token in the previous video that's bracket S bracket. And they are denoted in the training when they end, the end of the page, the internet page, or the end of the document that's being used for training, and that's slash s bracket slash s bracket. So the LLM has an idea, just like it's sees the end of sequence token, the slash s token, as any other token in the token list. So At some point you will see that the end of session sequence token will pop up in the list of logits. And at some point it will be even more likely that kind of increases. And yeah, when that is selected, yeah, that is the end of the answer, and that's exactly like where the LM stops generating a response and just hands back the whole the last token to the client. So this is we've gone through the basic route through LLMs. So the transformer produces logits. The transformer and tokenizer are deterministic. We add randomness to make it feel more human-like, and randomness is handled through a couple of settings: the temperature, top K, and top P. And again, this process is iterative. So once we've selected like the next token, the whole sentence is fed again into the transformer to start all over again. I do want to thank Ray, Joe, Natasha, Ryan, and Roderick for their feedback on the talk. If you like to experiment with local AI on your computer, do consider like downloading Pico AI Server. It's a free download. It's a free app. It uses MLX, so all the cool stuff that Apple open sourced, and it allows you to run like models like DeepSeek, Llama, and soon also the new OpenAI model locally on your computer, or serve it on your local AI network to family or like co-workers in a company. So you can find me on Twitter and other social media as Ronald Bennett. I do want to ask you if you want to see more videos or on this topic. Do tell me where I should go next. Things that we could discuss next are like the transformer, our black box that we haven't discussed yet in more detail. We can also see how we can implement all the things that we just learned in MLX using Swift, for example. And I just want to love to hear like from you what you want to see next. So do leave a comment, and thank you for watching. Really appreciate it.